this is Extractions&Ire, and welcome back to my shed in my backyard for some more lead-based entertainment. Today we want to make some more cool glowy things. So we want to make Perovskite nanocrystals, and they'll be highly fluorescent under UV light if we can get it right. So we've got this bulk Perovskite, which is this lead-based semiconductor material, and we're going to grind it down to make these tiny crystals, which should be very bright under the UV light. If that works, we're going to try and see if we can change their emission color by changing the material just a little bit without destroying it all. So if we can make the nice green fluorescent material out of this cesium lead bromide, then maybe we can make a red cesium lead iodide and a more blue cesium lead chloride. So that's the goal today, to make some fluorescent Perovskite nanocrystals. Our starting point is this cesium lead bromide, which we made, nearly a whole year ago in an episode where we tried to make nice big crystals of this cesium lead bromide from the hardware store. You may have seen it. It was the one with the birds, if you can't remember. Actually, if it was a whole year ago, does that mean the birds are going to come back? The birds might come back. Don't get me wrong, I do love the birds, but it's just a bit concerning to have baby birds around when you're doing lead chemistry. When we previously made this cesium lead bromide perovskite crystals, we lacked a certain chemical to continue on with this nanocrystal synthesis, following this paper from, I think it's 2017. I now have some oleamine, so we can finish and see if we can finally successfully make these nanocrystals. But before we get into the practical aspects, I always find it's easier to appreciate the synthesis if we have an understanding of what we're actually really trying to do and what is the science behind it. I know, we're going to speed run this. Some solids in the world are conductors, right? So the electrons are all shared between all the atoms in the lattice. Some materials are insulators, so the electrons aren't shared between the atoms, so they don't conduct electricity. And then you've got the secret third class of materials, which are semiconductors. Normally insulators, you can excite an electron, and now that electron is in the conduction band and can move around. When we've displaced this electron, we've got, now a positive charge and the negative electron. They are attracted to each other. When the negative charge recombines with the positive charge, we then release light back out again. These perovskite crystals are a semiconductor, but if we put UV light on it, we don't get any fluorescence light back out again. So a much more technical question is, why does making these crystals small make them fluorescent when they're big, they don't fluoresce at all? The first thing we've got to do is just get rid of this model. I hate these diagrams with the dots and the circles. It's weird to think about exciting an electron in this diagram because you're kind of like, well, where's it going? You can put it somewhere else in the diagram to kind of show that it's excited, but where, like, geometrically is the electron and how does it? I find it's easier in this context to think of electrons as probability clouds, right? So what you're doing when you're exciting an electron is that you're changing its 3D geometry. We're obviously just going to depict this in 2D, but in semiconductor material, what we're doing is we're taking say an insulating sort of isolated geometry. We're exciting that electron. The electron geometry, the potential is changing, so now it overlaps with the other atoms. So now it can freely move. That potential can be sort of shifted across to this same potential, but over different atoms. This excited electron, which is now in the conduction band and is free to move around, is still attracted to the place that it left behind. In this case, it's called a hole rather than a positive charge. It's kind of an absence of an electron. It's a whole thing. I'm not going to get into it. It's a whole thing. Oh, good bit, no. Ideally, in our case, we want this electron to come back and interact with the hole, and then we get our light back out again. But actually, fluorescence is kind of a random process. It's statistically random on, a one electron scale. So really, it does take time. The electron is free to move, so it just pisses off, right? Even though it's kind of attracted to that, it can go, right? And if it goes away, it can find other things to interact with, whether it's the surface of the crystal or a defect or just sort of lattice vibrations, can basically take the energy out of the system, so we don't get it back as light. So even though we have this charge separation, we end up with no fluorescence. So this is what's happening in the bulk state. And I will note, if you're trying to make solar panels, this is actually a really good thing, because you want this electron to piss off from the hole, because you want this electron to go all the way out the material through some wires and then through your Bitcoin miner or whatever. Electron separation is really good for solar panels, but bad for fluorescence. So once again, how does size make the fluorescence happen? Well, we're actually making the crystals small enough that the electron doesn't really have that many places to go. And even the distance it can travel across all the crystal, it still feels the influence of that positive charge. So it never really loses coupling with, the hole. And because they're sort of paired and the hole is attracted to the electron and the electron's attracted to the hole and that can't break, what you refer to this as an exciton. So by preventing this exciton from breaking up, you get very good fluorescent yields. This is great for us. It's not great for many people. And I think it's probably the main killer of solar panel yields is this exciton. But I've joined the war on the side of the exciton, Why not? Fuck it. I love light. One slight quirk of perovskites, which is different from other semiconductor sort of nanomaterials, is that the color of the emission, so the band gap of the material and the light that's emitted from there, isn't size dependent. And I don't quite know why that is. Once we're below that threshold where we can retain this exciton, we're always going to be the same emission color. So we should be able to see the same green that's in the paper as long as we get the actual chemicals crushed below a certain sort of size threshold. That's the end of the theory, but from a practical point of view, we've also got to consider that maintaining crystals of this size, getting them to this size and maintaining them there is quite difficult. The material will want to stick together, conglomerate, and it's got all these surface states which also can destroy the exciton. So that's where our oleamine comes in. It sort of what's called passivates the surface, which can do this thing with the charges, so the electrons that piss off don't decay so easily. Also, the particles themselves don't interact as much. So in terms of long-term stability and also fluorescence yield, this oleamine helps a lot. So if we're following the paper, the first step we actually have to do now that we have our perovskite is make oleamine bromide. So we have to make the salt of oleamine, and this just helps to add bromine into the structure or not take the bromine out, because we don't want to destroy the perovskite as we're grinding it. We don't want to break down the material, and the material is a little too easily broken down. So step one of this synthesis, well, maybe let's say step two, is to work out how to get this oleamine bromide. Step one really is, how are we grinding these bloody things? Because in the paper they use this plenary mill, which is this really upright, fast, advanced machine, which I absolutely do not have. I have a rock tumbler. Step one is equipment upgrade. Step two is oleamine bromide. Then we can do some grinding. And then finally at the end, we want to do some color changing. We want to take out the bromides and replace them with iodides, which we may or may not be able to do. But if we can do that, if we can exchange these ions, we actually change the overall material, which does change its emission color. Once again, not making any promises, because I don't even know if we're going to get past step one. This is Extractions&Ire. I don't know if it's going to work. You don't know if it's going to work. There's a lot of lead. That's it. Too much science. Let's go mix some chemicals. Okay, so to crush our crystals down to nanocrystals, we need a ball mill. Paper we're following uses a plenary ball mill, which is a very fancy ball mill. We don't have that. We have, it's really a tumbler, right? Like, it's for polishing of minerals and stuff, but we're using it as a ball mill, using it to grind stuff down. But yes, this won't be appropriate for what we need to do, because we've got to put solvent in and we only have a small amount of material, and this is rubber. So if we start putting in toluene in here, it's just going to soak into the rubber and just destroy it. And all these metal steel balls are probably going to contaminate our beautiful lead crystals with iron, and that might ruin the fluorescence. So we can't really use this, but I want to use that part. So I got a new container. There's probably a name for it. Anyway, it's over here. Here is our ceramic container. I think they're called jars. And I also got some ceramic media. Alumina ceramic bowls. Look at these, the fanciest bowls you've ever seen. Yeah, actually, the point is they're not actually the fanciest bowls you can get. This is expensive. This was a couple $100 for all the media and this jar, but it's nowhere near the most expensive one. This is not particularly hard. It's reasonably hard, but you can get like stabilized zirconia ones, and that costs twice as much. This was a couple $100, and you're starting to push $1,000. And then you can start doing things like tungsten carbide, which is very hard and very resistant, but you start to push several $1,000s for this. And you need your jar, your your outside container to be the same hardness as your balls. So you can't just mix and match and get the really fancy media and then the not so fancy jar. So this is a range of sizes too, which is, I think, better for grinding down to these small particle sizes. So we've got a bit of a mix here. So we'll be using this. It kind of works on the on this tumbler. I've obviously put this electrical tape on there to try and make it a bit smoother. I'll put it on and show you what the issue is. Hold on. It's not too loud. It's a little loud, but it's okay. I mean, it's turning. That's a good start. But this lid is not. I mean, if we have solvent in here, this lid is just gonna leak solvent everywhere. So we've got to work that out. But anyway, this is probably the entire budget for the video is just in this new media and stuff, but necessary to do it. Of course, reusable once we clean all the bloody lead out of it. Yeah, this is what we'll be using to crush down our crystals into nanocrystals. We'll make it all worthwhile if it glows. That's the hope. Great, so we've got lots of different sized media. One issue is that we got to really mix media with liquid, which is not going to seal particularly well in this lid, but I've got an ingenious solution, of course, as always. Look, this is slightly tilted so that when this goes here, hopefully all the liquid doesn't leak out the top here. We might have to just tape this closed, but yeah, if it's on this slope, hopefully it doesn't all just drain out. It does mean that this thing hits this little bit, but you know, it's nothing a little electrical tape and Teflon tape can't fix, so it's just jank enough that it might work, you know? I say with no confidence, but I think this is good enough for step one. Let's bloody get to step two and check out this bloody oleamine time. All right, after a very long time, we finally have some oleamine, which we're going to react with hydrobromic acid to make oleamine hydrobromide. Here we go, 70%. All right, let's get him out of there. Let's have a look at him and what it smells like. It might smell really bad, I don't know. It is an amine, so I am expecting it to be reasonably stinky. And here it is. It is sort of not really a liquid. It's a bit sludgy. I think, well, actually, I just looked up the melting point, and the melting point's about 26 degrees. So the room temperature it's quite cold today, or outside. It's sort of semi-frozen. It's a 70% solution, so in water. It's not particularly fishy, but it is very, not piss smell, but just like the kind of cleaning ammonia smell. The clean kind of, I mean, it just smells like ammonia, really. We've got about 20 mils in there and another 20 mils, and we need to react this with hydrobromic acid following the preparation from one of these perovskite papers. Actually, the main perovskite paper, I think, that we're following here with the mechanosynthesis one. There is a slight catch that we made this hydrobromic acid last time, and we know it's not 48%. It's not the maximum concentration the hydrobromic acid can be. And also our oleamine is only 70% in water, whereas in the paper it's kind of a vague 80 to 90%. All this extra water won't affect the ability of the hydrobromic acid to react with the oleamine, but it will affect our ability to collect the end product because the oleamine hydrobromide is quite soluble in water, so if we react it all together and there's heaps of water, even though it will make the salt, it won't crystallize out at the end of it. Instead of ethanol as a solvent, which is what is used in the paper, we are going to be using isopropanol, which is 100% isopropanol, and then we can boil it a little, and isopropanol has an azeotrope with water, so that means when it boils it actually carries off a significant amount of water. Actually, I think it's the azeotrope's about 70% isopropanol, 30% water. So if we put in a bit of extra solvent and then boil off some of that solvent once the reaction is done, it should carry off quite a bit of the water that's kind of residual from all this and hopefully crystallize out our product. That's my vision for this anyway. Hopefully that works. So I think this should be reasonably straightforward, but I don't know. The oleamine already is kind of yellow. It just goes yellow over time. Our reaction has kind of already gone yellow, and I haven't even done anything yet. Only other weird thing about this reaction is, well, we're obviously going to heat it in a flask in this heating mantle. The last time I used this heating mantle, it was smoking because I spilt all this toluene all over it, you know, during the last cubane reaction. So actually, before I mix any chemicals, let's turn this on and see if it works. Unless it works perfectly, I think I've got to throw it in the bin because there is quite a lot of power that goes through here and I don't want it to shock me. And also, look at me, I run a serious business now. So as soon as I spilt the solvent on it, I immediately bought a replacement. So if it is starting to look like it will hurt me, which is a distinct possibility if we've corroded some of those wires in there that drive the heating mantle, I am throwing it in landfill, which is what I should do anyway, but I believe in this. You know, the toluene is dried out. Maybe it didn't corrode any of the wires. Maybe this is still fine. It's a resilient little guy. Maybe. Does it even turn on? See some scorch marks. I'd love to see it. Let's move the flammables. It turns on. Okay, good start, it turns on. Let's see if it heats, and not by putting my hand in there. Okay, it is getting warm. It does stir. But, well, that fog is on the outside, right? Is it? Yeah, that's... Yeah, it's still steaming. I don't really like that. Yeah, let's use a new one today. Let's use a new one. This obviously has a lot going on in there still. There's obviously a lot of liquid in there. It's basically a steam bath now, you know? Let's use the new one. Just kidding. I can take the lid off. Such a dumb setup. This is so stupid. I just want to boil off the isopropanol. I just don't want to do it in an open beaker without any sort of column to separate out any boiling off hydrobromic acid. But this is stupid. This is so stupid. Look how it's sitting. That's so stupid. Looks like we're above the azeotrope temperature, so all the water's been removed with the isopropanol. It's gone a bit yellow, but actually very piss coloured. You don't need a focus to tell that is piss coloured. That's piss. And we're left with this nice white powder. It's hard to get it completely dry. I've been heating it a little bit under vacuum, but we've certainly got enough here. Even if it's not a great yield, I didn't even bloody work out yield because, you know, this ain't a numbers channel. Who gives a fuck about the numbers? How I avoid bad yield is just by not calculating. Anyway, whatever. It's a lot of powder. We don't need very much for each batch of bloody nanocrystals. So now we have this, we can go back to wherever the hell the ball mill is and actually start thinking about making nanocrystals and not this sort of side work. But it's always nice when it comes together. Ooh, drop it immediately. Must have contaminated the outside of the vial somehow, but man, it's slippery. And I was a little worried about it because, you know, this piss colored liquid comes out and you worry when you don't see crystals immediately that I've stuffed something up, but it looks good. So now all I have to do is keep this dry until the next stage, which is very easy to say, but the lab is kind of flooded. Yes, when it rains, it really does get very wet in here, and it really did rain recently, so I'm just fucking standing in this health and safety nightmare anyway. Don't look at that. Don't look at this fucking puddle. This is where you're looking. Hell yeah. And not the table either. Is the roof clean? Don't look at the spiders. All right, I'll block out the spiders. Look at that. Now that's quality. Shit. Fantastic. We have everything we need. We have our bulk perovskite, which we made last time. We have our ceramic media. We have our greasy bottle of surfactant that we need and a little bit of solvent. We're just using toluene, which is not the best solvent from the paper, but is definitely one that I have. So I'm still optimistic that it will work with toluene as a solvent. So really all we have to do now is mix all this together, put it in the grinder and grind it for a little while, and we'll get some fluorescent nanocrystals. But I gotta say bulk perovskite is looking a little worse for wear. The perovskite itself is this bright orange color, which is the cesium lead bromide, but the perovskite is not particularly stable, as I keep saying, and wants to break down into cesium bromide and lead bromide. And if we look at the two cesium bromide and lead bromide, they're both white. So we can see it's kind of returning to a white color, or a mix of these orange crystals with areas of white as it breaks down. So it's looking a little worse for wear. It's been covered in the foil, so it hasn't got a lot of sunlight, but it has been a better part of the year. But now I have to admit something a little embarrassing, because you see this breaking down and you think, maybe, I mean, if you're very intuitive, you might think, hey, what are the chances we're making nanocrystals just by the decomposition of this pure phase? And here I have this UV light. Look at it glow. Look at the green. It's a little hard to see perfectly, but look at the green. So the whole premise of this video being, let's take this bulk perovskite, grind it down until it glows, and now our bulk perovskite is just glowing green. Anyway, that's exactly the color we were expecting. That is the perovskite cesium lead bromide green. So this is potentially the simplest and easiest Extraction&Ire video ever, because it has simply worked without us doing anything. I can publish this, right? You know, advanced synthesis of nanocrystals by abandoning your product in a shed for 11 months. It's okay, cool. It's pretty bright, but I think we can do brighter, so it would be still good to grind these. But there is a section from the paper that says, alternatively, you don't need to make the bulk perovskite. You can just grind the two bromide salts together with the surfactant, and that will form the perovskite and the nanocrystals. It's of a little lower quality, but I think it'll be cooler to... Oh, look at the red from in here. I wasn't expecting this red. Interesting. And whatever that is... Ugh, gross. Okay, I think it will be cooler to grind two non-fluorescent things together and see it turn fluorescent, although now the green has to compete with this red of the ceramic. Why is that so red? I gotta start shining a UV torch on things before filming these episodes. Okay, so this is what we're gonna do instead. We're gonna weigh out small amounts of both of these, small amount of our surfactant, a bit of solvent, grind it together, and see if maybe after an hour or so, it forms these fluorescent nanocrystals, because we have no idea if it's actually working or not if we start with this, because it's already glowing, which once again is just so ridiculous. I said at the beginning of the video that, oh, the bulk perovskite doesn't fluoresce, and here it is fucking fluorescing. Okay. The chemistry just wants to be inconvenient, even if it means it's more inconvenient if it works. Goddamn, chemistry's an enemy anyway. All right, we've been on the grind for about 40 minutes. The smell of toluene in the room is quite strong, so hopefully, the solvent hasn't all leaked out and hasn't all dried up. So I don't know, I'm optimistic that maybe we'll see some green flecks in here, but it does have to compete with the red from the... Am I even allowed to upload an Extraction&Ire video if it works this well? It's just been 30 seconds of silence as I decide, whoa, it's perfect. That's sick. That's so sick. Okay, let's get some out. That's sick. That's so cool. Just gonna add another splash of toluene just to pull some more liquid off these media. I should be able to. And now the torch. Yeah. Hell yeah. Not quite as green as, oh, I suppose there's less suspended in the solvent now I've added more solvent, but I mean, I've got heaps of this material. What if I just scale this up like 10 times? Why don't I add, yeah, because I've only added a few tens of milligrams. What if I added 10 times the amount and just grinded it a little bit? Won't add 10 times the solvent because it'll leak out, but 10 times the solid. Let's try that out. Okay, so 10 times the amount ends up being just over 500 milligrams of the 2 bromide salts together. Chuck him in there. And this is just over 200 milligrams of the oleamine bromide. So we'll chuck her in there. And I don't know, I'm getting confident now. Just a tiny little splash of solvent again. Yep, all right. And then you could see somewhat on the camera, see where those white flecks are of the unmixed material. We'll let it go. Let it go for another 40 minutes. That seemed like the magic number. Let's get this shit on again. Back on the grind. All right, so this has been going for another 2 hours or so. It's very yellow in there. I suppose we've made lots of material. It's yellow until we put the UV light on it, and then it is very green. A lot going on. Anyway, that's fantastic. Actually, what is also interesting is this was our previous sample, and you can see all the perovskite has settled out, well, at least most of it, into this nice yellow layer, which is very, very bright. You can see all the green is, even when I have the light very far away from it, all that green fluorescence is coming from that solid down the bottom. We get a little bit of blue from the solvent, maybe from some other contaminant. So if we can wash these solids and maybe make it even more green, well, at least get this green purity a little bit better without this kind of bluiness from the solvent. If we can let this stuff settle out and concentrate it, that's even better. Oh man, I should wait till it's dark and hit this with the UV. Fantastic. All right, and let's collect more of this and let's get it settled out. And then if we've got lots of this, which we definitely have, we can think about trying to change its color with this ion exchange. I'll be honest, I haven't really looked into that much because I didn't think we'd get this far so successfully. But let's do it. Let's collect all this and then let it settle out, and then we can look at ion exchange. Well, it's very yellow though. Why does it go yellow? Why does everything go yellow? Who knows? Hard to demonstrate just how bright fluorescence is because I don't really know what the camera's picking up, and I could just be turning up the brightness on the camera. To compare, I've got some of the most fluorescent household objects you can find. If I turn off the lights and I've got my UV torch, we can see the sort of brightness of these objects. Really, it's the dish soap that's the brightest. Quite green, it's got a lot of dye in it. Post-it note is quite bright. The turmeric is a pleasant yellow, but is not super bright. These are some of the brightest household objects. But we can compare this to our perovskite, and it's potentially brighter than the dish soap. It is extremely green. I mean, it's lighting up the whole room with green. It's crazy. The camera doesn't quite know what to do with all this color. I don't think I've ever seen something as fluorescent as this. I've seen a lot of fluorescent things. Okay, let's try out some color changing reactions. We have our perovskite here. It's actually been about 5 days since I made these samples, and I was very worried about decomposition, but they are still very fine. This is the washings we had. It's kind of bluey at the top. I mean, it could just be impurities like the oleamine or something fluorescing, but could also be very, very small colloidal bits of perovskite. I've obviously spilled a drop here, and even the bits that have been out in the light for the last 5 days still glow very brightly. Actually, I washed this media a few times and it's dried out, but I'm never going to get my balls clean, honestly. They're going to be glowing green forever. But we got very bright green, and this is cesium lead bromide. How do we get other colors? Well, we need to change that bromide out for another anion. If we change it out for chloride, we'll shift the band gap of the material towards blue, and we should get a blue fluorescence. And if we change it out for an iodide to do cesium lead iodide, it'll shift towards the red, and we'll get this red fluorescence. But this is not a salt, you know, it's a solid material with these bromides in the crystal. So we're going to try out a method from 20 2018, there's quite a few different methods to switch them out. And in my opinion, a lot of these methods, I'm surprised they work at all, because you've got this solid material and you want to switch out the anions without breaking down the overall crystal. And it does damage the crystal. In a lot of these papers show before and after kind of this post-synthesis modulation. And a lot of time the crystals do fracture or go smaller in size. But the fact that you're still able to change out an anion within this solid matrix without completely destroying the crystal is quite impressive. It works at all. But we do need the cesium salts, because if we try and use, say, sodium chloride in and mix that in with our cesium lead bromide, although those bromides are going to change out for the chlorides, we're also going to change out some of the cesium for the sodium. And that is such a big change in size between the ions that it will cause the perovskite structure to completely collapse. So we will destroy our material. So if we maintain the cesium levels and put in a different anion, we should be able to change out those anions, or maybe even form a mix of the two anions within the structure, which will still shift the band gap. And so this paper from 2018 uses a sonicator to mix an aqueous solution of the salt and a suspension of the perovskites, or like a colloidal suspension of the perovskites, in hexane. We're going to give it a shot in toluene, because they're already in toluene, and I got my bloody ultrasonicator here, which is really not meant for science and sounds like you're trying to commune with an alien. It sucks to listen to on the video and in real life. Anyway, let's see if we can get this to work. There's our suspension of the bromide perovskite in toluene, and I'm just going to add some water. It should sink to the bottom. Perfect. And here is some cesium chloride I made, I'm going to say 2 years ago, but it may have been 5 years ago or 6 months ago or something. So we just have some cesium chloride already here. I made it from hydrochloric acid and cesium carbonate. Let's just add a couple of crystals. We're just winging this because my confidence is high at the moment with the chemistry, and maybe we'll turn the UV light on. We'll see if it changes colors just straight away. Still looks pretty green to me. So let's get it in the sonicator. I'll get the lid on here. Turn it on. Alright, confidence was high, but let's give it a few minutes. Paper wants it to run for a few minutes, so we'll let this run. Alright, I added more water and a bit more cesium because nothing was happening. Still looks kind of the same green, but let's give it a bit more time now. Still the same. Okay, it's had 10 minutes of sonicating, so I've got to think of something else. Maybe the hexane is an essential part of it. So I've got this cold shellite from the hardware store, which is mostly hexane, so close-ish. Then I'll just put a drop of the toluene suspension with the perovskites in it into this. It's already got the cesium chloride solution at the bottom. That aqueous solution has a couple of cesium chloride crystals not quite dissolved yet, but with a stir they'll definitely dissolve. Oh, another drop of lead. I'm really got to decontaminate this place afterwards, but okay, now let's see if I can get this in the sonicator and see if this one changes colour. There's our two, it's the same colour. Well, it doesn't look like it either, but I'll keep it going. Okay, I was about to give up on this. I didn't really see that much change over the first 15 minutes of sonicating, so I dumped in quite a bit more cesium chloride into both of these, and I've been sonicating it for the last half an hour, like additionally to the first 15 minutes. I've had 45 minutes of sonication. I was just hoping to see maybe a subtle color change. Are you ready? Look how blue it is. One of them's gone completely blue. One of them's gone that bluey green. Of course, compare it to the normal green. We've got kind of a bluey green. And a full blue one. Hold on, I'm gonna get the other camera. Once again, it's too bright. That's crazy. I wasn't expecting this to work. Oh man, nothing is ever gonna work again in this lab after the success we've had in this video. This is a terrible omen. All right, that is so sick. Oh, I'm so excited. I need to make some cesium iodide. I don't have any cesium iodide on me, but I have some cesium carbonate and some iodine. So maybe we can cook up a potion that will let us turn this red as well. Now, cesium iodide is not a particularly common reagent. It's not a reagent I have lying around. Actually, well, it's a common material in that it's very often used in radiation detectors. You get these big cesium iodide crystals, and when your gamma radiation goes through, you get scintillation, and you can use that to tell the gamma peaks of your radiation detector. But taking a very expensive, large cesium iodide crystal from a radiation detector and smashing it up just to dissolve it in water is a little too barbaric even for me, and I've done some barbaric stuff over the years. We are going to try and make some cesium iodide. We have some sodium iodide here, but I can't really think of a nice way we can add cesium ions to this sodium iodide and get pure cesium iodide out again without all these sodium ions floating around, which will destroy our perovskite, assumably. Assumably is not a word. In that vein, we will run with some optimism and just try that anyway. We'll just make up an aqueous solution of sodium iodide and mix that with our perovskite and sonicate it and see if it goes a little red. But trying to make some cesium iodide, I have some cesium carbonate, I have some iodine from, you know, the stockpiles of reagents somewhere. It's held up better than I thought it would for being pretty old. It's just under some water, some iodine crystals. So once again, optimistically, I think if we just mix some cesium carbonate with some iodine, reflux it a little, we will form some cesium iodide in solution. Also a bit of other weird chemicals, oxidizers like iodate and, you know, I say you know, but I don't know. I'm assuming you don't know. But if we just boil it, then maybe most of the anions in there will be iodide, which is good because I don't really know what iodate is going to do to our perovskite. Might destroy it, might do nothing. So a little bit of experimenting here, you know, just doing some potion making. Why not? So cesium carbonate and a little bit of water with some iodine. Let's see if we can reflux that. Well, just boil it, see if it goes nice and clear. We've got some demineralized water. Coles Simply demineralized water, product of Australia. Look at us go. And they say Australian manufacturing is dead. Look at us go. Demineralizing our own water. That's sovereign capability if I've ever seen stuff. Yeah, look at us. Hell yeah. We're independent. All right, fuck it. Let's do some chemistry. Yellow, but clearing up. After 10 minutes of sonication, both of these solutions, this is the one with the sodium ions and the one with the cesium iodide, well, hopeful cesium iodide. Yeah, both of them are a bit messed up. They've gone red. Maybe there's a hint of red fluorescence. Actually, I mean, look at that. That's glowing red. That sort of did work. What? Yeah, that one didn't work. So maybe the sodium iodide isn't as destructive as I thought. It's obviously not as bright. So it is getting wrecked in there, but not as wrecked as these ones because it just looks like it's a fine white powder. It's actually all left the organic layer altogether. Probably precipitated out lead iodide or something. But that's a promising sign. I wonder if we can sort of combine these two, like have some cesium iodide and some sodium iodide and just see if we can get this red fluorescence a little brighter. We've obviously exchanged out some of the anions for the iodide, but we've just also kind of destroyed the framework a little, which is why it's so dull. That's my guess. Okay, I thought about this a little bit longer, and my cesium iodide solution, well, my supposed cesium iodide solution, the one that caused really quite significant decomposition in the perovskite, it was extremely basic, you know, when I checked the pH, and it's really, you know, a consequence of me just trying to force chemistry to work that definitely won't work in terms of the iodine reacting with the cesium carbonate. I was boiling it and trying to reduce some of the iodate that would be formed, but yeah, I don't know, it was getting really basic, so I tried to adjust the pH more neutral with some sulfuric acid, but then the iodate reacts with the iodide to make iodine. You see that as that yellow brown. So I was kind of going in circles for a long while. I dried out the solution, tried to decompose the iodate that way. This sort of vibe-based chemistry sometimes doesn't work because you can't just have an idea of how chemistry should work and it does it. But I eventually added some sodium thiosulfate as a reducing agent, which will reduce the iodine down to iodide and still give us a reasonably neutral pH. The downside, of course, is that we added some sodium, which I was trying to avoid, but I couldn't really find a good reducing agent that I have on hand that would do that well. So we have this solution now. It's absolutely chocked filled with cesium ions, a little bit of sodium, and iodide. The pH is neutral, so let's give it another shot in the sonicator with this solution. It's a little bit cloudy because the thiosulfate does produce some sulfur, which is kind of colloidal sulfur, so actually we'll check if that glows at all. It's got a bit of a blue hue to it, but we're still trying to chase this red color here. Let's get everything together and chuck it in the sonicator one more time. I've got to stop panning the UV light over this desk because then you can see all the contamination. It's like bringing a UV light to a hotel room and feeling all disgusted, but you know, in this case I'm bloody spilling lead everywhere rather than spilling. You know what I've always said? I'd rather be shooting lead than firing blanks, you know what I mean? I could see that on a bumper sticker, you know? I'd rather be firing lead than shooting blanks. Fuck. Alright, let's get this fucking chemistry on it. It's maybe a slightly different green, like a deeper green, but yeah, it's definitely decomposing once again. And it's definitely not red. So the best success we've had so far is still just with the sodium iodide, which makes this red one, which has a faint red glow. So why don't we just try something along those lines again? Forget this weird cesium solution. Let's just flood it with sodium iodide. Let's flood it with sodium iodide. Alright, this is cesium bromide and sodium iodide. It's about 50-50 just by volume. It's once again just on vibes. The idea here being here that we've got some cesium ions already in solution, so maybe we won't pull so many cesium ions out of our framework. So if you can replace some of the bromides in our structure with iodides, we should still see a shift to red even if we don't completely get to the red end member. So let's give this a shot. Oh, I've just added it and it's changed colour straight away. Oh, what? I didn't even need a sonicator. Huh, that was quick. Oh man, I have to decontaminate this whole area, but damn is that pretty. Once again, they're not as bright, but god damn is that red. Wow, that was quick. So we managed to get some color tuning, but the stability of these products isn't that great. I mean, I made these ones about 5 days ago now, these blue ones, and they've been in contact with the water, so I think they're more prone to decomposition. There's still some blue, but it's nowhere near as bright. And these orange ones, we never really got super bright. In fact, maybe the first attempt was the best one. Anyway, the final thing I want to try out with these is my stretch goal of making some films out of them, because obviously we can see that they start to decompose, and we haven't had a lot of decomposition in about a week or so since we've had this lead bromide one, but over time and exposure to air and light, it's going to break them down, and we can dry them out as we've seen from the contamination on the bench, and they do stay glowing, you know, when they're not in solution or in suspension, but that will fade. However, how do we get them into a film? Well, if we just mix them with a polymer and then set the polymer, then we should have something that glows very nicely. And there's some papers that do this in a PMMA film, a polymethyl methacrylate powder, which sounds a bit fancy, but that's just the name for acrylic, and you can get acrylic powder very cheap for use in like fake nails and nail art. Now, you might have just had the idea of, wow, you can make really cool glow-in-the-dark nails with this. You could have nails that glow under the UV light. No, you've forgotten about the lead in this. Your brain craves the lead. Got that idea because you want to be exposed to lead. But that's a bad idea. No rave is worth lead exposure. So we're not going to be painting our nails with this stuff, but I want to dissolve up some acrylic. It should dissolve in the toluene, which our stuff is suspended in, and then we can flatten it out, let it dry. The polymer should be there, and then we want to pull off that polymer to have this nice flexible bit of film that glows really brightly. We obviously have to peel off that film, so I've just got this Teflon beaker. Hopefully we can let the solution dry on here, and then the Teflon should be non-stick enough to peel off the film. That's my goal here. So let's do a dry run, as in a run without any lead in it, and see if we can make an acrylic film and get it off the beaker before we start mixing the lead in there. Here's some toluene. Just got some warm water. Just getting it nice warm in the warm water. How much of this acrylic powder we can dissolve in there? That's an acrylic smell. Looks like it dissolved. Solution's getting thicker. Alright, that looks about all that will dissolve, so let's pipette a small amount onto our nice Teflon substrate. Sure, let's use the word substrate. Okay, it needs to dry a bit longer. Got potential though. It has potential. Oh yeah. Oh yeah. Hell yeah. That's it? Perfect. No colour on the UV, that's it's just acrylic. Don't know what the hell is on those tweezers. It's not lead though, for once. Alright, let's add the lead. A square. Ah, fucked up the square. Alright, let's try this out. Yeah. Oh, hell yeah. Oh, are you seeing this shit? Final test, does it glow? Yeah, I'm thinking it glows. It is very yellow. It would be cooler if it was completely clear and then it turned green, but I'll give it a pass for being yellow because look at this thing. It's just a green torch now. Fantastic. This project has been so successful that we actually finished before it's spring, so before the birds came back and tried to build their nest again. Well, actually the nest is already there, but before they came back and started laying more eggs. So no birds this episode because of success. So I hope whatever you do goes as well as this, whether it be firing lead or shooting blanks, you know. I hope it all goes well for you. It's time to decontaminate and get a lead blood test. Cool.